Okay, so we're going to talk about simulation. I think it's something that we've done a few times, but I haven't really explained it much. Another way to think about what we're about to do is sort of like a crash course in Stat 428, like computational statistics. And it's not necessarily something we directly need in this course, but since it's something that we've used occasionally and understanding it better will lead into our next actual course concept, we're going to go ahead and talk about that here. So first we need to talk about the setup that we are almost, the setup that we use in most problems in statistics, which is we're thinking about a random sample from some population, and that random sample is of size n. So what I have here is a bunch of notation, and I'm going to explain sort of each step of it. So first we see, hopefully you can still hear me when I'm talking sort of down. Let me know if you can't. So first we see these random variables. And this notation means that they are IID random variables from some population. And we're using this notation here for the population distribution. I cannot type, or not type, but write today. So you can think of that as either the PDF or the PMF of some known distribution parameterized by theta. It's not important, the notation so much there, but it's just a way to represent a population distribution. Okay. And then one of the more confusing things we always do in statistics is we have uppercase, in this case, xi's, and lowercase xi's. So the uppercase are random variables, whereas the lowercase are realized values. But that's also a little weird too, because we don't actually see the values. We just see these placeholders, x1, x2, and so on and so forth. So what I call those is potential realized values. So those aren't the actual data, but it's a placeholder for data. But so the lowercase values are not random, but the uppercase values are random. It's an odd distinction, but it'll be sort of important in a second. And then what I wrote down here is just some random numbers, as if, okay, so we actually got a random sample from some population, and here's the data we got. So those are actually what we call the realized values. Okay, so then what we've been doing sort of all along in this class is estimation. So there could be sort of qualities of the population that we want to know about. And the one that we're almost, just laser focused on is this idea of the mean of a population or the expected value of a single random variable. So this here is a parameter that we're interested in. So even though we have x1, x2 through xn, when we know we have a random sample like that, often we sort of refer to x as like a generic random variable that has the distribution of that population. So this expected value of x is something about the population that we would like to know. Okay, and then we talked about, in this class and in every other statistics class you've ever done is, well, okay, how do we estimate that with known data? And I tried to draw it a very particular way. So this X bar here is intended to be a capital X bar, and that is what we would call an estimator. And so something we need to note here is that an estimator is just a fancy word for a statistic. And a statistic is a function of the sample data. And when we view the sample data as random variables, x1 through xn, well, this is then a function of those random variables. So this also is a random variable. And because this is also random, that means that it also has a distribution. And that's going to be a lot of what we're interested in right now. And so we're going to come back to that. But the next x bar, which hopefully I wrote small enough that we view that as a lowercase x bar, that is the same exact formula, but by virtue of them being small x's instead of big x's, these tell us how to compute the estimate given the data. So what I say there, how to compute the estimate. So for different data sets, this is, you insert data set, it pumps out an estimator, and that's this last thing we have here. This is the estimate for some made up data set that I wrote down there. So plugging in numbers to that expression. So I just wanted to sort of go over this notation because we're going to sort of focus on estimating parameters of some distribution. So what I have here is a list of potential parameters. And something I want you to start thinking about, if you haven't before, is that parameters are a function of the population distribution. Meaning that we could take these four quantities, the expected value, the median is the second one we defined there, the probability that an observation is bigger than 8, and the variance. And if we apply those parameters to different distributions, we get different results. So like if we calculate the expected value of a normal distribution, like a standard normal, the mean would be 0. But if we calculated the expected value of, say, a binomial distribution where n is, 10 and p is 0.2, the mean would be 2. So depending on the distribution, you get a different value of the parameter. So the next column over is estimators. And estimators, being statistics, are functions of the data. So we're not going to go through how these estimators were derived. But so the natural estimator for the population mean is the sample mean. The natural estimator for the true population median would be the sample median. That's what this notation I've used here is. A natural estimator for the probability that an observation is greater than 8 is using the empirical distribution function. In other words, here, counting up how many of the observations are greater than 8 and dividing by the number of observations. And then lastly, we have a potential variance estimator, but we're not going to focus on that one as much. Okay, so we have these estimators to estimate these parameters. Then the question becomes, well, what are the distributions of these estimators? So the only way we're going to know those distributions is if we know the distribution of the population that we're talking about. So as an example here, let's think about a specific case where we have a random sample of size 25 from a normal distribution with a mean of 5 and a variance of 9. So I kind of gave away what one of the values is here. Let's think about these then. So we want to estimate the mean. So we're going to use the sample mean. And I think this one we might all know. The distribution of the sample mean, x bar, is again normal with a mean of 5 and a new variance of the population variance divided by the sample size. That's something that you've seen over and over again, including in this class and others. So that one we knew. That's kind of okay. We figured that one out just fine. But what but what about the rest of these? And what I'll say is we could absolutely derive the distribution for these next three estimators, but I really don't want to. So for the median, this would involve order statistics. So like if you've taken 410, the math behind that is probably flooding back to you, and you're not enjoying that. For this probability estimator, that actually wouldn't be too bad. So I think if you realize that this part here, if we know the population distribution, we could calculate that probability. And then we have, and it's either true or not. So it's kind of a Bernoulli thing. So we kind of have like this sum of Bernoulli thing going on. But I don't want to do that. And the last one, let's see. Pretty sure this has something to do with chi-square. But I'd like to reemphasize that I'm not good at math. So what I want is a way to come up with these distributions of these estimators without having to be smart and be good at math, neither of which I am. So let's come up with another way of doing this. So the idea I want to put forward here is something called Monte Carlo simulation. So essentially, what we're going to do is we're going to repeatedly generate samples from a known distribution and then calculate the relevant statistic and then look at the distribution of those. So the first thing we need to do is we need to generate a sample of size n from the population distribution. And you might be wondering, well, how do you do that? It kind of seems like we're asking for some magic to happen here. And I submit that that's fine because R can do that. We've seen this a little bit before, but anytime you use like R and then some distribution name, functions of that form, those are generating random observations from a known distribution, and that's what we're going to use here pretty heavily. How that happens, like underneath the hood, is something that we're going to ignore in this class. That's what something like 428 is for. We're just going to, believe that magic works and does what it's supposed to do. You might remember at the beginning of this class, there were some issues where random number generation was not working the same for some students versus others, even with the same seed. And that had to do with our changing how that worked underneath the hood. But that's not important here. So essentially, we get a random sample. And because we're going to be talking about repeated random samples, I'm going to use superscripts to denote like, okay, this is random sample 1, 2, 3, and 4. And so then with each of those samples, you'll calculate whatever statistic you're interested in. So say you're interested in the sample median. Well, for each of those things, you calculate the sample median, and then you repeat that a lot of times. And then, so I'll use R here. So this will be the Rth, that's a weird word to say, Rth simulated statistic. So we can then use those to estimate the distribution of the statistic using the empirical distribution function of those statistics that you just generated. This will become a lot clearer when we fire up R in a second and actually do this. But schematically, sort of visually, it'll look something like this. So we start up at the top with some known distribution for the population. Okay, so then from this population, we want to generate random samples of size n. So what we see here along this left-hand side here is our first simulated sample. And then we can calculate whatever statistic we're interested in on that sample. And I'm using S for statistic. And then we're, that's a function of the data. So I'm putting the data into there. So this is the statistic calculated on first sample. And then we just repeat this process a bunch of times. I'm using R for the number of times we repeat this. So we have 1, 2, yada, 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 R samples. And then on each of those samples, we calculate the same statistic repeatedly. So that's a general idea. So I think it'll be a lot easier to understand if we do this inside of R. So let's move over to R. Okay. So I first want to do an example with a normal distribution. I'm going to try to write big enough that we can see it up. Wait, where is that? We can see it in the top right corner there. Let me know if that's not the case. I'm realizing I'm going to have to move some windows around on my computer, but we'll get it to work. Okay, so let's do something like this. It's the same example from earlier, but now we're going to do this. So the first thing I want to be able to do is, I guess I need to specify n here instead of having a generic n. Let's do samples of size, let's do samples of size 16, so we have some difference in numbers here. So just if you can't see that, that is an n of 16. So first, let's verify for ourselves that we can actually do this. So hopefully this is working and you can see that keyboard. I'm not going to specifically talk about the keyboard shortcuts that I'm using here, but hopefully since you can see my keyboard input, you'll see some of the keyboard shortcuts I'm using. But we might do a separate stream and a separate recorded video just on specifically keyboard shortcuts, but I'm going to try to not highlight those, but at least let you see them along the way. See if I remember them. Okay, so I'm using R Markdown here, but so we want to use the R norm function, and that's random normal. So I want to simulate samples of size, 16 with a mean of 5 and a standard deviation. So the R norm function uses standard deviation instead of variance, but so if the variance is 9, the standard deviation is 3. Okay, and we can do this repeatedly. So each time I do this, it generates a different sample of size 16. Just for the record, if we did something like this, I don't want to do that. I want to do this. I can't. Okay. So notice that I keep rerunning the same thing and it keeps getting me the same answer. So that's sort of how seeds work a little bit. But so essentially when I'm doing this and it keeps giving me a different sample, that is effectively getting to the second row here where we're repeatedly generating those samples. Okay, so we'll do the mean. So we'll consider some parameters and some estimators. So we're going to want to estimate the true mean, and we know what the true mean is, but we still want to do it. Let's also look at the median. I'm going to use this notation for the true median of x. And this notation for the sample median. And then I'm going to let's do some probability. So let's do the probability that x is greater than 6. And so we're going to estimate that with something like this. Okay. So those are the 3 parameters that we're going to be interested in. And we also have the 3 estimators. So something we can do is actually, and this will be sort of useful to think about, we can calculate the true value of those 3 parameters. Like in practice, we wouldn't be able to do this, but because we've specified the distribution, we know these things. So the mean is just 5. We already know that. So if I want the true median, that would be Q norm 0.5 with a mean of 5 and a standard deviation of 3. So that's the true median, which is also the mean because it's a symmetric distribution. And then if we wanted the probability that x is bigger than 6, we would do P norm. Q is 6. The mean is 5. The standard deviation is 3. And we do not want the lower tail. We want the upper tail, so lower tail is false. So these are the 3 quantities that we're going to try to estimate. And we can estimate them with the estimators we outlined here. So for the first one, we would do the, let's store a sample here. And because we want to see it, we'll put it there. So we now have x stored in our environment. You can't see that, I guess. Let's quickly. So we have x stored in our environment. Right. So again, by creating a sample, that didn't change the parameter values. But so the mean of x would be the sample mean of x. The median of x would be the sample median of x. And then if we did, let's see, x bigger than, 6. And we want to find the proportion of trues here, and that's if we use the mean function. Okay. So these are the true values. These are the estimated values. This one seems a little off, but that's just totally possible because of the variability in randomly generating a sample. So we could keep rerunning this first line here, and we see we get different answers down here. So what we really want is to say, well, what is the distribution of the sample mean? What is the distribution of the median? What is the distribution of this estimator for the probability that x is bigger than 6? Well, so what we're going to do is we want to do this. So we want to repeatedly generate samples. And then let's say, let's first investigate the mean. So I want to each time calculate the mean of that thing. So what I really want to do is this. So what I'm doing here is equivalent to the bottom row here now. I'm just repeatedly generating these statistics calculated on these randomly sampled, these random samples. Okay. But so I want to do this a bunch of times, and I don't want to have to keep clicking, and I want to store all of these things. So this is where there's this really nice function called replicate. And first let's do it with just 100. So what I'm going to do, what this replicate function does is it says, well, do this thing 100 times. So if I run this, so these values here now are, the equivalent of 100 of these s of x i's that we see in the slide there. Okay. So I want to store that. We'll call these x bars. Okay. So now we can say, well, let's look at a histogram of those things. So this sort of in and of itself is an estimate of the distribution of x bar. But I want to do a lot more observations here. So what we're really going to do is we're going to generate 10,000? Yeah. 10,000 random samples of size 16 from a normal distribution with a mean of 5 and a standard deviation of 3. And then for each of them, we're going to calculate the sample mean, and then we're going to store it. So run that. Check it. That looks like a bunch of sample means. Okay, cool. And then draw the histogram. Okay. And it should be sort of no surprise that this looks extremely normal. Why? Because as we said earlier, this sample mean we know has a normal distribution with mean of 5 and a variance of 9 over, what is it, 16? And we can sort of verify that with these x bars. So if we look at them, so if we look at the mean of the x bars, it's pretty close to 5, which is, what we see here. If we look at the standard deviation of the x bars, it's close to 0.75, which, again, I'm not good at math, but I think that's pretty close to 9 over 16. And so what you need to realize is that oh gosh, we gotta get rid of this. If we essentially made this number bigger and bigger and bigger, these numbers would become closer and closer to the true values of the parameters 5 and 9 over 16 for the x bar. We could also look at things like, well, so we know that distribution. So if we did something like p norm of, let's say, 4 with a mean of 5 and a standard deviation of the square root now of 9 divided by 16. So that's the probability that a randomly selected sample mean, or, so we take a sample, calculate the mean, is less than 4, is like 0.09. Now let's look at the mean of the x bars less than 4. Pretty close. So essentially what we did was, like, supposing that we didn't know that x bar also followed a normal distribution and what normal distribution it was, we could use the empirical distribution of these x bars that we created as an estimate for that distribution of x bar. So let's do that really quickly for the median and this randomly chosen probability here. So let's remember that the true median is this value here, and for some randomly chosen sample that we had done earlier, that was the sample median. So I basically want to repeat the same process. So I'm going to steal some code for myself. So I'm now going to say this is called medians. And instead of calculating the mean each time, I'm going to calculate the median. So these are a bunch of simulated medians now. And I think this might not shock you. This distribution also looks incredibly normal. I don't know what this distribution is off the top of my head. Like the true one, over here, we could overlay the true distribution. Maybe I'll go back and do that at the end here. But looks like pretty similar, huh? This one looks a little tighter. But anyway, so this then would be an estimate for the distribution of the sample median. And like, let's say, okay, well, what's the probability that the sample median calculated on a random sample of size 16 from that normal distribution is, let's say, greater than 7. So we could do the mean of those medians greater than 7. So we estimate that there's like a 1.3% chance that we get a random sample of size 16 and it has a median bigger than 7. Okay. So I also wanted to do that probability. So that probability that x is bigger than 6. So again, just stealing code from myself again. So I'll call this probs. So this time, well, actually, we shouldn't jump ahead of ourselves. So what we want to do is, so again, here's one random sample. So we want to say, well, we want the probability that that random sample is bigger than, was it 6. Okay, so that would be our estimate given just that one sample, but we want the distribution of this estimator. So it looks like we need to do, okay, let's do it like this now. So here's our code to do, a random sample. So if we do mean of this bigger than 6. Okay, so basically that's the thing we want to replicate. So let's steal it and put it here. We can get rid of this. Okay, so this is sort of roughly what that distribution looks like. We see some weird little things here, but it's roughly normal, but with some weird gaps. Okay, so this could be applied, to any distribution, right? So again, we said that the these parameters are really a function of of this distribution here. So we could do a different example where instead of normal, let's say that we were looking at an exponential distribution where let's say, hold on a second. So first of all, let's look at the exponential in R. So, okay, so they use this rate parameter here. So the mean is going to be 1 over that. But so we'll do exponential with a lambda of, let's say, 0.5. So I think that'd give us a mean of 2. Okay, so now if we consider the distribution of these parameters, and we'll just look at the mean this time because it's different, right? So now we don't have this normal distribution anymore. We would have that mean and that variance, but it wouldn't necessarily be normal. It would get closer and closer to normal if we had a bigger sample size, but with a sample size 16, I have a feeling it's going to look kind of normal, but not super normal. So let's see. So we're going to do random samples from an exponential distribution. We're again going to do a size of 16, and I set a rate of 0.5. So here we are generating the random samples. And I just want to look at the distribution of X bar because I don't know what it is. And we could maybe do some math to figure it out. We knew if the sample size was like really big, it would be approximately normal. But let's use this Monte Carlo thing. So we want to calculate the mean with a bunch of these things. So here we're repeatedly generating a sample, calculating the mean. So we want to replicate this, let's say 10,000 times. Again, the more the better, because then you get a better estimation of the empirical distribution of, in this case, the sample mean. We'll call this exponential X bars. Run that. Have a look at some of these. Okay, so that looks like it worked out okay. And now let's look at a histogram of those. Okay, so it's unimodal. It's not quite symmetric, so I wouldn't call this normal. But and I don't know exactly what the distribution of X bar is, but when the rate parameter is 0.5 and the sample size is 16, this is a reasonable estimate for the distribution of that thing. So again, the empirical distribution using these would be how to do that. So if we wanted to do something like say, well, what's the probability that the sample mean is greater than, let's say, 3? So we would do exp x bars bigger than 3, I said. And then we'd want to find the proportion of those where that's true. So there we go. So if we had to if we didn't know how to do the math and we wanted to come up with the probability that a sample mean of a random sample of size 16 from an exponential distribution with a rate parameter of 0.5 is bigger than 3, this is how we would do it. So this is I don't know, it's kind of a useful way to substitute computing know-how and power for mathematical ability. So this is sort of like how simulation studies are done. These again are very simple ones, but this is the general idea that we're going to mess with in the next video. So I'm going to stop this one and sort of get ready for the next one.